This session, I'm going to introduce you to multiple regression. That's regression in which you have multiple input variables, so you end up with a prediction equation that has more than one input. The data that I have here is a really tiny data set, so that's not good from an analysis perspective, but from perspective of being easy to work with, it will be good, and it'll also get you away from analyzing housing prices in Seattle, and this time we're going to analyze something that you're more likely to buy, and that's a bottle of wine. Here's the situation. A few years ago, somebody developed regression models that were able to predict the price of wines better than the experts could predict, and this was quite a breakthrough. And these days, those kinds of things are commonplace, where a model outperforms the experts, whether it's in the game of Go or reading chest x-rays or whatever. You see something of that nature in the paper almost every day. So here's the problem. You bottle wine, but then it's I think put into wooden barrels for a while to age for a few months, and then you take it out of that and you put it into bottles to age for a few more years. And somewhere in that early part of the process, probably when you take it out of the barrels, the experts taste it, and it tastes pretty awful at that point. But somehow they have to predict, is this going to be a good year or a bad year? And by good year or bad year, we're going to measure that by the price at which the wine sold later. So the data that we have shows a particular type of wine that was bottled in the years through 1960 through 1969, so we've only got 9 data points, and it shows the price at which that wine sold in 1991. And that's going to be what we're trying to predict. So right off the bat, I'm going to point out one thing that's not the point of this lecture, and something that you don't need to understand. I'm just pointing it out for your information. If we were to do a histogram or scatter plot or whatever to analyze the prices that are listed in column B there, you'd notice something very funny about them. 1961 price is about 5 times some of the other prices in the data set, and 1966 is also about double what most of the other prices are. But in particular, 1961 is an outlier. And in a big data set, you have a choice. You might just eliminate the outlier. For example, in our houses prices, if we had a house that sold for 20 times all the other houses in that zip code, we might just say, well, that's a special case and we're not interested in predicting this. But when we're talking about wine, the ones we really would like to be able to predict is the ones that are going to go to the moon. So if I have wine that's going to sell for $5,000, I don't know if that's per bottle or per case, probably per bottle, I don't know. Then I would like to be able to predict that. So something that you can do when you look at your histogram and you see that it's not bell-shaped, you see that it's got outliers and everything, something that you quite often do is rather than use the price itself as an input variable, you take the natural logarithm of the price. And for those of you who haven't seen a natural logarithm since you were in freshman math, we'll talk about that later. But another way you could think of it is all we're doing is compressing the numbers so that the big ones get squeezed in to be more consistent with the smaller ones. Another thing you could do is just take the square root of all of those numbers, and then you wouldn't have such a wide dispersion and such a asymmetric distribution. So don't worry about that. We're going to predict the log of price, and if I can predict the log of price, I can convert that into an actual price. Now the two input variables are harvest rain and summer temperatures, and this is based on expert knowledge that when it's hot and when it's dry, the grapes are, I guess, not as watery, and so you get more body to the wine. And something else that supposedly happens is there's less acid in the grapes, so that also gives you a better taste. So hot weather, dry weather is good for wine. So with global warming, we're going to be drinking a lot of really good wine in the future, I would assume. So the first thing that I need to do is build a single regression model. Let's pretend I had 10 variables, 10 input variables. It would be tempting just to say, let's put them all in there and see what we get. Well, what you're going to get is going to be garbage. Excel will handle up to 10 input variables, but here we've only got 9 years of data, so if we put 10 input variables, we'd probably get a perfect fit, but it would be totally meaningless and nothing that we would want to use. So what we tend to do, or what I would recommend, is we start with the most simple model, and then we add terms to that model, and if adding terms makes it better, then we keep those terms. If they don't, we don't put them in. So the first thing I want to do is to decide which variable I would want to use as my input variable. So I'm going to compute a correlation matrix, so I'll go to my data analysis here and select correlation, and I want to compute the correlation between the log of price, harvest rain, summer temperature. I used a label there, and I'll just let this land as a new tab in my worksheet. So there is my correlation matrix, and the variable that is most highly correlated with harvest rain is with the natural log of price is harvest rain. In other words, and it's a negative correlation, so that basically says the drier the weather is during the harvest season, the better grapes you get. And if I were to square that, I would get an R squared of about 0.67. And then I look at the other input variable, or potential input variable, and that's summer temperature, and I could also square that and see what the R squared is there. And that's about 0.5. So basically it says knowing harvest rain would explain about 2/3 of the variation in the natural log of price, and knowing summer temperature would explain about half of the variation in natural log of price. And you're saying, hey, wait a minute, now that can't be possible, because if I add those two together, I get a number bigger than 1. Well, what's going on here is that those two variables, harvest rain and summer temperature, contain a lot of the same information. So if I have one in my model and I add the other, I have a lot of redundant information. And the way that I know that is true, other than the fact that they both sum to something bigger than 1, is the fact that the correlation between my two input variables is about 0.5 or minus 0.5. So it says the hotter it is, the drier it's going to be. In other words, as summer temperature goes up, harvest rain goes down. And excuse my coughing, I'm just getting over a bug here. So what that tells me is I really can't say for certain what I'm going to end up with when I put both of these variables in there, because they contain a lot of the same information. And it may be that once I have one of them in there, it's not going to help much to add the other one. But we'll investigate to find out. So I go back to the data, and remember that harvest rain was the one with the biggest correlation coefficient. So the first thing I would want to do is to build a regression model with harvest rain as the input and a natural log of price as the output. So I'm going to go to data analysis. I'm going to select regression, and my input range is natural log of price. The input, or the X range, is harvest rain. By the way, those units, I don't know what they are, probably centimeters of rain or something, I don't know. And the summer temperature, I assume, is in Celsius or whatever. This was all the data that I could find, and it wasn't very well explained. The data has labels, and I want to get all of the nice plots and everything, so I'm going to plot the line fit plot, and it'd be okay to look at the residual plot, and let's just do them all. So here's what I get, and here's harvest rain line fit plot, and what I see there is that there is a strong negative correlation, as we already observed. As rain goes up, the price of the wine goes down, or the log. This is the residuals, and it says for different values of harvest rain. This is remember, the residuals are the error, the difference between the actual and the predicted price. And we don't see anything really strange going on there. When the harvest rain was really, really low, we had the biggest error, and we might want to investigate that later. But for right now, the most interesting number, well, this is the formula down here, and it tells how I could predict the log of price. And if I can predict the log of price, I can raise e to that power and get the original price, but don't worry about that. Right here is the thing that I am most interested in, the adjusted R squared. So that number right there tells me how much of the variation I was able to explain, and that shouldn't be a surprise to you. We've already figured that out from our correlation matrix, that R squared was somewhere in that neighborhood. The R squared we got was this number up here. And this adjusted R squared, what it's really doing is taking into account the fact that we have such a small sample size. We only have 9 observations. So we have to be kind of conservative in saying how much of the variation we are explaining. So now we're ready to do a multiple regression model. So we go back to our data, and let's see what kind of model we get if we were to include summer temperature as an input into the regression model. So I'm going to do regression again. And the only thing that's going to change this time is, rather than just harvest rain, I'll have both harvest rain and summer temperature as inputs. And I get OK. And several things you want to notice here. The adjusted R squared increased. We expected that, but it didn't increase nearly as much as we probably hoped it would. And that's because, if you know harvest rain, and it's low, that's probably telling you it's a hot summer. So you already have a lot of the information you need. You have your model here showing you the intercept and the two coefficients for the input variables. So the most fundamental question that we have to deal with is, should we stick with, by the way, here are all the plots. There's summer temperature versus the price. That's harvest rain. Here are the residuals, or the arrows, as a function of both summer temperatures and harvest rains. And we see as summer temperature goes up, the price goes up. As harvest rain goes up, the price goes down, and the residuals look okay. But the one thing that I want to compute here is the increase in R squared from adding the extra variable. Because if R squared is not going up a whole lot, we'll talk about it in a minute, but there's no point in adding another variable, because there's 3 or 4 reasons why we wouldn't. But let's compute that. That is the current R squared, and I'm going to subtract from that the R squared that I got in the single regression. So that. And so we got about a 10% increase in the adjusted R squared by adding another variable. So that number there might make us at least consider having a model with 2 variables in it. And in fact, the model that is used has even more than 2 variables, and it has a lot more data. It's got data from different types of wines, different regions, more years than what I have here, and so forth. But anyway, what I would probably conclude here is explaining another 10% of the variation is worth adding another variable. But if that improvement had only been, say, 3 or 4%, I would be strongly tempted to stick with the single variable regression. And here's why. There's something called the principle of parsimony. You want to remember this. The principle of parsimony says you want to be very stingy with the number of parameters in your model. And there's several reasons for that, and they're illustrated here. One is, if you've got a small amount of data, you do not get as good estimates of the model parameters when you have more variables in your model. For example, this matrix down here with all the coefficients tells standard errors and upper and lower values and so forth on that. That sort of tells us this is the range in which the true values of those parameters could actually lie, and those ranges get wider as I add more variables into my model. So one reason for sticking with a model that has fewer parameters, unless there's compelling reasons to add more variables, and the compelling reason would be it explains a lot more of the variation. The adjusted R squared is a lot smaller, is that you don't get as good of estimates of your parameters when you add more variables. So that's reason number one, estimate the parameters. The second reason is more of a practical one. It's really easy to explain a model that only has one input. You can literally say for every increase in harvest rain, every centimeter increase in harvest rain drops the price of the wine by so many dollars or euros or whatever. And so that's really easy to understand. It's really easy to explain. When there's 3 or 4 or 5 variables in there, it's not as simple and it's not as intuitive. The third reason is basically the confidence we have in a model. If I can take a model with only one parameter in it, let's say, and make accurate predictions on the data that I currently have, then I'm much more confident that I can make accurate predictions on future data. On the other hand, if I have a model that's got 10 inputs into it, I know it's going to fit the current data well, but being able to confidently say that that's going to work in the future is an entirely different thing. So it's a lot like physics. In physics, when you're trying to explain a phenomenon in physics, you bias your thinking toward the most simple model that will explain what's going on, and that's the one that's most likely to be the correct model. So, principle of parsimony: better estimates of your parameters, number one. Number two, easier to understand and explain. Number three, more confidence that it will work on other data sets or that it will work in the future. So, in general, the way you build multiple regression models is you start with your most simple model and you bring in variables one at a time and you look at that adjusted R-squared to see how much improvement you get. If you get something that's practically significant, in this case 10% is practically significant, then you would keep the additional variable. If you get something that's kind of decimal dust, 3 or 4 or 5%, you probably are going to be saying, I don't think it's worth making the model more complex and less reliable to try to pick up that little extra improvement in the prediction on this particular data set, because on future data sets it may not even perform as well as the more simple model. Okay, so that is all. Multiple regression is so similar to simple linear regression that it's not a big leap to understand, and the techniques in Excel for doing it are very similar. So I hope this will be enough to get you ready to go. And in our next assignment, you're going to take your baseball model in which you've predicted runs per game as a function of on-base percentage, and you're going to add other variables in like slugging percentage, batting average, and a variable representing the league to see if that's given you enough improvement to make adding those variables worthwhile. So thank you, and that's all for today.